Okay, I was thinking about a very low-key title, so I came up with this. So I want to see, after we did our first work in sparsity, what we can do next. And I'm going to talk about some of the works we have been working. So what are the next couple of frontiers we can do? Obviously, we have a little bit of foothold into sparsity. We want to look at more algorithms, more data types, and how to get more users. So let's look at more data types in here. So if you look at what we can do, this is something like a DGM kernel we can actually do, but there are things like triangular matrices out there. There are matrices that have symmetries. There are graphs with special patterns like diagonals and blocks in here. Databases, of course, come with many interesting patterns. Things even like run length encoding provides an interesting opportunity. There's a pattern in there that's not just sparsity. And also things like convolution with top-class matrices. Also, you can think about this as doing linear algebra with sparsity in here. How can you represent these things? So if you look at a simple thing beyond sparsity, if you look at this kernel in here, if you just look at simple sparsity, when you don't represent zeros, we get level format like that, compressed level format like that. But instead of using zeros, if we say the most common value is 1, and if you say if you do fill value 1 and not implicitly represent 1, we actually get a little smaller matrix in there. But the more opportunities, actually there's runs in here. So if you do run length encoding of this one, you can get a much better compressed representation in here. So the idea of a run length encoding is you can think about it as the fill value is the last value I had. So it is a run in here. Instead of it's not a 0, it's the last value I saw gets repeated for the until the next value that I get in here. So that is basically what run length encoding. So we can actually do that as a representation in here. So this is very interesting because if you look at compression, what they have done in here, what we can do is kind of merge these very different domains of lossless compression and sparsity. So if you think about these two examples, so doing this MRI has both zeros and ones. So if you just do zeros only, you don't get that much compression. But on the other hand, do run length encoding, you do a lot better compression in here. Again, same thing with this video. In the compression community, they'll be happy to get this. But then when they operate, they will basically make it dense. On the other hand, if you operate directly on compressed data, the same way do sparse computation, actually we can get a really interesting speed ups in here. So we can push in here. So this is one area that we want to expand beyond sparsity, just do run length encoding. What else can we do? So if you have all these different patterns, now we have to compete on these darn things. And how do you go about competing on adding something of a sparse matrix and a run length encode matrix? So we need to think about a little bit deep on here. So I want to go back to just figuring out how we do computation. If you do dot product of two dense matrices in here, we do basically both are dense. We just iterate over that. This is something we have been doing for last 50 years. On the other hand, if one is, and this is the computation, if one is sparse, and the sparse is represented using the IDX and val matrices in here, what you can do is you iterate over the first sparse matrix and then look up the dense one. When you do that we can do here, and you get a code like this. And then if both are sparse, we do this two-finger merge in here. We go and finding non-zero values, iterate over that. This is great. So this is the code we are going to get there. But how about if the second matrix is a dense region in the space in here? So you have a sparse, total sparse there, and something that has a dense region in here. Of course, we can do it the same way we did before, but it's pretty damn inefficient to do this in here. The right way to do this would be, and this is the code doing that, right way to do this would be, basically, go look at the beginning of the dense region. You can do a binary search in the first one to say where the dense region begins in here. And once the dense region find, it's a dense sparse multiplication. So you can just iterate over sparse and look up in the dense region until you run out. And that's a much less amount of computation to do something like that. So what you want to do this here is generate code like this depending on co-iteration pattern in here. So what we see here is if you do dense and sparse, we do dense, we know how to do that. If you dense sparse, we do gather, and sparse, we do this two-finger merge in here. And you can have lot more other patterns going on in here. And you can keep adding patterns in here. So Taco did these two. And something like Halide can do dense one direction or only, and but other loop can be many different things. You can generate code. And something like Cora did dense and ragged combinations in here. One thing we are looking into is any possible combination. If you're going to co-iterate how to generate code for this, I think this will give us a lot more breadth on what we can do in here. So another interesting thing we want to look at is how to deal with dynamic data structures. So this is derived by, so if you want to PageRank computation of this very large 1.6 million number of non-zeros, this huge matrix, and to 2.55 million, 255 million number of non-zeros, this is in log scale, the amount of time it takes to PageRank. It's great, but now we want to add one element into that thing. It's as expensive as doing PageRank because now we have to copy the entire darn matrix and do a lot of computations. So this doesn't scale if you want to change something. There are a lot of computations we actually want to change. There are things like dynamic graph processing, sparse neural networks, where actually the matrix has to be changed. So right now we have set of representation that's very hard to insert. Delete we can probably deal with by zeroing out element and doing a little bit of extra computation. But inserting element is extremely expensive in here. So one way we want to do it is looking at pointer-based data structures. And one thing we developed was this language to describe different pointer-based data structures, linked lists, C-trees, D-trees, and stuff like that. And within that, also generate co-iteration code in here. So one data structure could be pointer-based, both could be pointer-based or pointer-based and dense, and then generate code in here. So I think this is a way we can get into a bigger domain and trying to handle more users in here. So now I want to switch to different frontier, more algorithms. We have always focused on einsum expressions. How can we go beyond einsum? So here's an interesting thing. Assume you want to do convolution. Obviously convolution is not einsum, but there could be multiple types of convolution. So you can have filter sparse, you can have input sparse, or you can have both sparse convolution in here. If you do this convolution today, there are different libraries that focus on each type of convolution. However, each of these libraries have issues in here. So each library will do only one type or two types of convolution. They only support one format or only the CPU or GPU in here. One thing we want to do, and we are pushing is, okay, can you do convolution by extension to Taco? And by doing that, we can basically do every type of convolution, lot more formats be supported for the sparse side, and in doing that. So how do you do that? What Taco right now do in algorithm language, doing einsum, is you can do only single variable for any affine expressions. And you can actually do a little bit of a constant in here. So what we need to do is more complicated expressions that has multiple variables in here. And the way we can do this is basically treating one variable as a constant and then put outer loop around that variable. It's a pretty simple hack. By doing that, we can actually get these kind of convolutions done. And what we show here is by doing this, we can actually get pretty nice performance results in here. And if you compare these results into what people are using, things like submanifold, sparse convolution in machine learning, in CPU, we get really, really good results because people haven't that much optimized on CPUs. On the other hand, GPUs, there's a lot of hand-optimized kernels out there. We are getting comparable results for hand-optimized kernels in here. So again, another way to expand what we can do, the expressions what we can do, we can actually encompass people right now don't look at our technology as a path for them. Another thing we are looking at is our group for a long time has had this two kind of very similar thing but not similar. So Taco, we did tensor algebra, einsum expression, multiple formats we can do that. Whoa. Okay, sorry. Okay. But the interesting thing about Taco is these are single statement, feed forward pipelines, and every time you do operation, you operate on the entire tensor in here. On the other hand, if you something like graph it, we saw some talks before that alluding to similar things. We have very different operation like push-pull kind of operation using user-defined functions. They're iterative, you're iterating over something, you're doing partial updates to the entire data structure. You're not updating everything, you have to do some kind of masking in here. And also sometimes you want to calculate multiple outputs in the same iteration. Otherwise, if you try to iterate multiple times, it's too expensive in here. So there were these two different projects our group has been running for a long time in here. And at the end of the day, they all work on sparsity in here. So one thing recently we looked at is, can we think about this thing together? Basically, how can we expand Taco notation to basically deal with some of these graph computation in here. So I'm not going to say too much, but we have a poster that's talking about how to expand Taco, how to put these outer loops and how to do iterations, all these things. So we will be able to do these high performance graph algorithms also from a tensor algebra point of view. So the final thing I wanted to is more users. So it's great, we are getting more algorithms, more data, but we also managed to get a little bit more users in here. So one thing users hate is complexity for our system right now. They have to provide algorithm language, a format language, and this darn schedule. So talk to somebody who's just a domain specialist and say, okay, you have to come up with a schedule. They're like, what's a loop transformation? And doesn't work in here. So we need to get rid of this one. So one way to do that is come up with auto-tuning. So we have worked on two types of auto-tuning. One interesting thing is in sparse computation, there are certain ways of running the computer that are asymptotically bad. So the first is asymptotic auto-tuner that figure out, okay, look, this computation might not be a class of computation that is asymptotically best. Pick one of those. Out of that, you don't get really bad results. So doing asymptotic tuning. Also, later there's a talk on more input sensitive tuning. So you look at the input tensor and look at the input pattern and from that actually tune the scheduling and format to basic suit in that. So by doing that, we can actually come up with really good schedules without really burdening the programmer. And the neat thing about system like that, now you can bury it very deep in a software stack. So you only need to deal with the algorithm in there. Algorithm is obvious, you need to do that, but the rest can be buried deep and we can deal with that. One place we want to bury deep is in Python. So if you look at Python, there's something like NumPy implemented on there, SciPy implemented in there. The amount of users using this is staggering. The huge number of programmers are touching this in here. So they have this system called PyDataSparse because SciPy has some support for sparsity, but not that much. NumPy has no support, but everybody wants to do this kind of array programming on sparse data. And PyDataSparse is looking to do that. However, if you look at PyDataSparse, the performance is pretty darn bad. We can actually, because the way it maps, it's not that efficient. It do a lot of data copying, a lot of inefficient computation. So if you actually can do these operations, we have shown by extending Taco, we can do that. We can get either order of magnitude or two order of magnitude sparsity in here. So one thing we are doing right now is we are working with Consite, who's the company that basically behind PyDataSparse, to basically try to see whether we can integrate Taco technology into PyDataSparse and get it to the hands on Python programmers. And at that time, we need to have auto-tuning because there's no way these Python programmers will understand what a scheduling language is. So we are trying to build that schedule. So I want to finish saying that there's a lot of really cool things we can deal with sparsity. And we heard a lot about machine learning, large language models. A lot of these things can really benefit from sparsity. Right now, I think they are just pushing their toes and seeing a little bit of sparsity, but not that much of wins because doing it in software is too expensive right now and hardware is coming up. But coming up with these general purpose compilers and hardware tech in there, I think can have a huge impact going forward. Okay, with that, I'll end my talk.